we'll walk into chapter 2. Chapter 1, we have given you a brief introduction, what to expect in the whole semester. Chapter 2 is going to be a bit more on a revision of what you have been exposed before, specifically space mechanics. As I've said, we are going to do, of course, dynamics and control. Dynamics control means that not only looking after the attitude of the satellite or spacecraft, but also the basically orbit side of it, which is the orbit control. So towards the end of this semester, you'll be exposed to even orbit control. So this is going to be a very big revision. I expect all of you have gone through space mechanics. Please do go back and refer. But what I'm going to give you a nutshell of what you need to have so that we are quite clear with the orbit and orbit control at the end of the lecture. All we know is Kepler was there. Johannes Kepler, he has helped us basically to define particular orbit in space. Technically speaking, he, as you can remember, had three of his law. Of course, the first law says that it describes technically not only the satellite, but it can be any rigid body circling in the center of a central body. So that also defines how a moon it is going to actually orbit planet Earth. So first law is that, and from first law basically you should be able to describe at least that eclipse without that eclipse lot, you can even actually define a shape of that particular orbit. So with that, technically we should be able to draw a particular orbit, and we can understand how this particular rigid body is going to circle around or orientate in a particular manner. Now, whereas Kepler's law 2 or second law, equal time equals space, means that if you look at an orbit, if you draw a two-dimensional pattern, you can see when you have an orbit, basically when you start orientating a particular central body from one point to another point, if you calculate the time and the particular area, it should actually have an equality with another part. So that also tells us, well, in that case, I should be able to calculate my time if I can use it cleverly. Now, unfortunately, it doesn't stop there. We have a third law. Yeah, the third law gives you basically is nothing but is an period. Now, it seems that Kepler's law 1, 2, and 3 of his laws can exactly tell you the time, which is not really true. Reason being, when you look at Kepler's law 2, it tells you the actual difference of a time, any time frame. So the whole problem of Kepler, I think if you have seen the lecture on space mechanics, is practically to tell you where you are in order for you to predict the exact time. So time needs to be given. Difference of time is easily to be calculated. So Kepler really cannot do his actually job in order for us to use it to determine the exact time at one spot. So therefore, another rule has to be actually applied, the Newton's law. So Newton's law has to be applied together so that we can solve Kepler's problem. That is the Kepler's problem. Kepler can give you the difference, but he cannot pinpoint you, tell you where this is the exact time. So in order for us to solve, we have learned that in optical mechanics, we have used the Newton's law to solve it. We have done that. Okay? So technically speaking, based on these three laws and Newton's law, you should be able to have an orbit done. And based on that particular orbit, we have also defined what exactly attitude is all about in chapter 1. How we define that attitude, how we define the orbital motion of the spacecraft, what is with orbital frame, what is fixed body frame or body frame. That we have defined that in chapter 1. So, but the basic of it, we need to define the Keplerian element first before we can start doing the body frame definition and the orbital frame definition, the local vertical, local horizontal that you have seen in chapter 1. Orbit model, as all of us know, 6 Keplerian elements. When I say Keplerian elements, please do understand perfect orbit, no disturbance. It's perfect orbit. So 6 Keplerian element, 1 time derivative, the rest are no. So 1 time derivative is your true anomaly. True anomaly gives you the position of the satellite or the real body or even the spacecraft in the particular orbit, in the Keplerian orbit. So very, very important to understand. It is a perfect orbit. As I said, unperturbed orbit, that means there is no perturbation. Remember, in space mechanics we have learned, we have defined Kepler's orbit first. That means with all the six orbital elements, we know how to draw an orbit in space. Then after that, we say that this orbit is not perfect. There are a lot of disturbances, and we have identified all those disturbances. For example, the solar, for example, gravity, for example, aerodynamic, and we have quantified that, and we have also established how these disturbances is going to disturb the 6 orbital elements, 6 Keplerian elements. When you disturb the 6 Keplerian elements, that means the orbit that you have, the ideal orbit, would not be ideal anymore, it will be non-ideal, therefore it needs to be corrected. The only way you correct it is basically to orbit correction. And we are relevant here in this subject because we need to help to correct this orbit by means of thrusters. Now, again, very classical, how you can define the 6 orbital element in space. This is what is shown. I think you have seen this also in space mechanics. Okay, all being defined with respect to vernal equinox, so as we know. Right. As you can see, now the idea of this whole ideal Keplerian orbit. Now the problem, as I said, we really can't find the actual time. In order for us to find the time, we need to actually have the difference. So mean anomaly came into the picture. So we have used basically the Newton's law. We have used the Kepler's law, brought them together, and we have deduced a method to estimate the mean anomaly. When the mean anomaly is estimated, then practically in particular orbit, the time can be determined. When the time is determined, it's done because the total period of the particular orbit, that will be given by the third law of Kepler. Having that, the particular time that is known, and when you know the particular time, basically your true anomaly in terms of degrees is also known. So what you are trying to do here, you know exactly where the spacecraft is done. So you need to pass by. You need to do this exercise basically to find basically the mean anomaly in order for you to get the actual true anomaly. This is again, it is a revision. Please do the exact calculation. I'm very sure you have done this estimation. You have done in your space mechanics. Okay, this is just to tell you the position. Why we have 4 different seasons. Now, luckily, if you are in equatorial motion, you are not worried about this. You don't have these 4 seasons. You will have only 1 season. Like in Malaysia, we have only 1 season. But if you are in the north or south pole, then the 4 seasons are very predominant. Yeah. So that is important to understand that. So that is the reason now, in order for you to control, in fact, we will see there are quantities like magnetic field is disturbing the spacecraft. We want to know the location of our spacecraft also. So the orbit definition is extremely important. If you are in equatorial motion, there are different sets of disturbances disturbing you. If you are in equatorial, there are different quantities also different. We must know this, okay, and we can plan it accordingly. Don't forget, in this case, basically, sun is you are sitting in the sun basically and looking at it. But on the other hand, assume that I am actually in planet Earth, I'm going to look at the sun, and this is what exactly happens. Okay, it depends where you are. So you don't have to worry. Assume you want to fly a spacecraft in the vicinity of sun, that will be your reference. In our case, all your cases actually you have seen in this chapter, or even in the previous subjects, especially space mechanics, the center is always a geocentric coordinate system. That means it's a center from planet Earth. So don't forget. Okay, simple definition. Now assume I have 6 orbital elements. Now from 6 orbital elements, practically we can define in a reference called IJK. IJK is Earth-centric. That means a geocentric coordinate system. I can define my R, which is the radius, and X, Y, Z. So practically, if you have 6 orbital element, you should be able to tell me exactly what is the exact radius that you are in. Having the radius, you should be able to define your semi-major axis already. And you should be telling me exactly what is the coordinate if you have the 6 orbital element. Now 6 orbital element, all of them are not high derivative except for what is that? True anomaly. So true anomaly changes the all your coordinate also will be changing accordingly. Yeah? Alright. Orbit perturbations. Now this is important. You will see that same disturbance are basically disturbing not only the orbit but also your attitude later. So we established, this is again a quick review. These are orbit perturbation, non-gravitational perturbation, aerodynamic. We have quantified that, and we know in space mechanics what are the elements which is going to be affected by atmospheric drag. Solar pressure is affecting you as well, affecting the orbit. Gravitational perturbation is basically, obviously, the Earth is not spherical, so you have a precision effects when you start actually flying, especially very near to planet Earth. So this is quite common. And third body. Now, if you are Earth-bounded mission, let's say very near to planet Earth, you can almost neglect the third body. That means it's a two-body problem. But if you are flying somewhere, maybe a moon mission, don't forget the third body. Third body will be a moon. Okay, and slightly further, then sun becomes important as well. So if you fly very close, and your mass is actually very small, a small satellite, we consider that as a two-body problem is good enough. Okay, we don't need actually a third body problem. So this is very important to see. The further that you go out of planet Earth, third body problem comes in very important. Okay. Orbit type, retrograde, LEO, GEO, all these have been exposed to. In any orbit you fly, attitude control is a must, period. Regardless whether it's retrograde, prograde, LEO, GEO, HELIO, whatever, attitude control is mandatory. You have done also maybe interplanetary missions. From planet Earth, you are going basically fly by Venus and then landing towards and flying towards Mars. Well, as far as the space mechanics is concerned, it's fantastic. We can do the delta V. We can calculate the delta V needed. But don't forget, while we are flying, we need to also watch our attitude. So attitude control is mandatory regardless of the orbit types. Regardless of the orbit types. Okay, you do the job just like, remember the chapter 1 we have defined your local vertical, local horizontal, your body coordinate. That will be applicable for all the orbit types, regardless where you are. It doesn't change. Okay? We have seen ground tracks. You can have any ground track. So when I said just now, regardless of the orbit type, it can be any shape. It can be circular, elliptic orbit, hyperbolic, parabolic orbit, very high altitude, Earth-bounded orbit, Mars-bounded orbit. Attitude control is mandatory. Now, if that is the case, regardless what ground track I could use, I know for the fact that attitude control is mandatory. Now, you see a very beautiful ground track. Huh? if attitude controlling is not there, you will have ground tracks like this. Because your camera might not be actually focusing well. Your camera might not be focusing well. Now assume that attitude control or other orbit control is weak. Okay? You can also have this effect. Okay? So it's very, very important. Okay? Now, this ground track is always associated with the orbit control. Orbit control. Okay? Now, if orbit control is off, this can be disturbed. Now, if attitude control is off, depending on the magnitude, total, maybe a tumbling. Okay? A tumble. Tumble means like it tumbles. Now, in this case, attitude control, look at this, tumbling at one point. Orbit control is okay. Attitude control is off. Now, this motion, attitude control is good. My mouse is actually counting, just showing them it's okay. But orbit control is gone. This, both are gone. Okay? So you must know. So in order for us to produce a good ground track, you must actually do an orbit control. You must, because why ground track is important? Because ground track tells you exactly whether you are supposed to actually, let's say, scan a particular place, scan Malaysia. You are supposed to pass above Malaysia. If you are not passing above Malaysia, then it's problem. Okay? And that's one thing. Second thing, when you produce, let's say, you do remote sensing. When you do remote sensing, you are flying nicely. When you look at the actual telemetry, ground track is very good. Excellent. Then when I look at the image, it is not looking at Malaysia, but you are looking at Indonesia. Means what? Attitude control is gone. Okay? So you are flying good, but you are tilted and you are looking at Indonesia maybe where you are flying. Okay? Or maybe you are looking this side. Okay? Maybe you are looking at Thailand. You are not actually looking at Malaysia. So it's important to understand. So when you analyze, that's why you say when you analyze a ground track, when you analyze, let's say, remote sensing data, you already know how healthy is the satellite. You can tell easily. Orbit correction and maintenance. This is exactly what we want to do. Towards I will expose to you not only on the attitude control, but also expose to you on that orbit control. End of this lecture, I want to have a very, very simple conclusion so that you can keep that conclusion of chapter 2 and bring forward towards the end of the semester where we want to use this and do an orbit control. Okay. Now, we know that to do orbit control or orbit maintenance, you have heard of north correction, south correction, east, west correction. These are typical in geostationary orbit. Okay? So look at it, altitude and plane. Now, out of plane is basically an inclination change. Inclination change, don't do it often. Maybe I told you, I think I told you before, once in a year maybe it's already good enough because it's going to cost you a lot of fuel. Okay? Then home planar basically is in plane. Is this one. Change of eccentricity. Let's say it's supposed to be a circular orbit, it becomes eccentric orbit, then you need to change it. Or it is supposed to be a circular orbit, it becomes almost like a eccentric orbit, elliptic orbit, sorry. It comes as a circular orbit, you need to correct it. Okay? So this is actually in plane and out of plane. Now, in order for you to do this, or we have learned one of the very, very simple one, or famous one I would say, command transfer, where you calculate the delta V, correct? Alright, this delta V is important. This is coplanar, and then for out of plane is also again another delta V that you do. You have done this exercise in space mechanics, okay? You've been exposed to, okay, you want to do coplanar maneuver, delta, can calculate delta V. You want to do a non-coplanar maneuver, can calculate delta V. Now, conclusion of all this review of space mechanics in this particular chapter 2, hold on to the delta V. Please remember delta V. Orbit control, I need delta V. Who's going to tell me how much I need? Space mechanics is going to tell me how much delta V I need, right? It is. So I know this delta V. So delta V is my input to as a control input. How the system is going to be, let us wait and see towards the end of this semester. Then you know that, okay, I need delta V this much. How I know? Space mechanics in onboard computer, technically you can calculate, or you can do this exercise in ground. You do all the space mechanics calculation. Exactly what you have done in your space mechanics, you do it here. And you know exactly how much delta V to fire or how needed. You send the command straight from your ground station to the satellite. Up, receive, telecommand receive, then it goes into the system, goes into the algorithm, it triggers a particular system, in this case a propulsion system. And we are going to see how this propulsion system is going to look like, how the loop is going to look like. So everything is interconnected. Huh? Everything is interconnected. Now, remember this, if you are not in the right orbit, even your attitude control is not going to help you. It's not going to help you. So you must be in the right orbit. So right orbit, we need to correct the orbit. So now you will see, so that is the reason the whole system, this is of course a spacecraft dynamics and control. If you look at the system level, more often than not, it is called ADCS, Attitude, Determination and Control System. So the control part can be orbit control, can be attitude control. This is what I've shown you in chapter 1 as an example. Okay, there is a loop which is going back for orbit and attitude. With that, thank you. We will do maybe some exercises in upcoming lecture.